For our next example, let's take our long line of charge with uniform charge distribution and let's just form it into a ring. So now we've got a ring shape. Let's find the electric field some distance away from the center of the ring. So that's our goal. We'll start the same way. We'll identify a little piece of charge on our ring. I'm going to call that dq. And what we'll do next is find the element of electric field, we'll draw it first, created by this little element of charge. So this little bit of dq will make an electric field at this point P. This can be a little hard to see because we're all in 3 dimensions now, so I'm going to try and model it. If this helps you, then by all means make this model at home yourself. I grabbed some pipe cleaners and I formed it into a ring. I have part of a broken matchstick to be my x-axis. I will hold it upwards. And if I'm going to take my dq right here, it's going to make an electric field that points away from that dq. So that's what that's going to look like. Twist it around, hopefully you can see it a little better. Okay, I know this is not ideal. Please, by all means, set this up at home if you wish. So our DE points away from that DQ. I'll try and get that in on the diagram. So I'll draw a straight line from DQ to point P. And my little element of electric field is going to point along that line and away from dq. Okay, I need to get my components in here. So my dex is forward, or in the positive x direction. Why don't I say that instead? That's a little bit more clear. My dey, since my dq is in the top half of the ring, dey is going to point straight down. There's my dey. And my DEZ, since my DQ is in the back half of the ring, my DEZ will point in the positive Z direction. So coming out this way. So my DE is a vector with components in all 3 dimensions. To find my total electric field, I'm going to have to take the sum of each of these components. First, why don't we pause and think about the symmetry a little bit? Is anything going to cancel? So we know that our EY is going to be the sum of all the little DEYs. Let's look at that one. So for my ring, any part of charge at the top half of the ring, so anywhere on the top half of the ring, the electric field is going to point down. Anywhere on the bottom half of the ring, the electric field is going to point up, okay? Top half points down, bottom half points up. That means for every piece on the top, there's a piece on the bottom where the y components are going to cancel. It's symmetric about the y-axis. Okay, so our net y component of electric field is 0. What about the z components? Well, if we look in the back half of the ring, the electric field is going to point forwards. If we're in the front half of the ring, the electric field points backwards. Okay, so that half points this way, that half points this way. So those x components are also going to cancel. Everything from one side will cancel with something from the other side. Ez is the sum of all the DEZs. That's going to be 0. And that's due to the symmetry of the ring. So the only thing that won't be 0 will be our DEX, or our EX won't be 0, because no matter where we are along the ring, it all points in the same direction in x. So the x component always points in the same direction, but sometimes the y is up, sometimes the y is down, that means they cancel. Sometimes the z is forward, sometimes it's backwards, they cancel. But the x's are always in the same direction. So the x is the one that's going to be non-zero. We'd like to get going on finding the electric field now. We know that the net y is 0 and the net z is 0. That leaves us with the x. So our total x electric field is going to be the sum of all the x components, or the integral. Let's see if we can sort out what that is. Well, let's get some geometry on our picture here. We know that the radius of our ring is given by a. So that's from dq to the center of the ring. There's a. We've already drawn r. That's from dq to our point P. So that's r. And then let's say that x is from the center of the ring to our point P. And we'll call that distance x. We know that we have to use trigonometry to find our x component. Let's label an angle theta. And I'll say that theta is the angle between DEX and DE. That means DEX is adjacent to the angle. We'll use cosine to find the x component. Okay, the next thing we can fill in is that we know DE is the element of electric field created by this small charge dq. So DE is k times dq divided by r squared, where r is the distance from the point to dq. What's our next piece we can fill in? Let's think about what r is. R is the hypotenuse of a right-angled triangle where the two legs are x and a. That tells us that r squared equals a squared plus x squared, or r is the square root of a squared plus x squared plus x squared to the 1/2. Okay, what about cosine theta? Cosine theta is adjacent over hypotenuse. It's x divided by r. So let's put this in for cosine theta and see what we get. So we get the integral of k times dq for r squared times x over r. So that's the integral of k times dq times x over r cubed. Okay, what next? Well, r is equal to a squared plus x squared to the 1/2. That means r cubed is a squared plus x squared to the 3/2. Let's fill that bit in. Equals the integral of k times q. Whoops, I dropped my dq there in the middle. K times dq times x over a squared plus x squared to the 3/2. Our next step in the integration will be taking our constants out front. So in our expression, k is a constant, x is a constant because it's just the distance from the center of the ring. A is the radius of the ring, so a squared plus x squared to the 3/2 is also constant. Then we're left with the integral of dq. This is kind of interesting. So now we have to ask, what is the integral of dq? The integral of dq is what we get if we add up all of the little bits of charge all around the ring. What we would get if we added all that up would be the total charge on the ring. So that means that our x component now is k times x over a squared plus x squared to the 3/2 times the net charge q. There's our x component of electric field. To find the total electric field, now we just have to write it as a vector. Which means we have to write it with an I hat for the x direction. So there's the electric field due to a ring of charge. For a homework question, and I'll give you some hints on how to get started and post the answers. Let's ask, find the electric field at the center of the ring. That's where x equals 0. So just plug in x equals 0. Part B, what is the electric field if we're very far away from the ring, but still on the x-axis? So for this part, you have to do an approximation. If x is really, really big, it means that a squared plus x squared is about equal to x squared. You can ignore the a squared term. So put that in your expression and see what you get for E. Part C, where is the electric field a maximum? To do this part, what you would do is you would take the derivative of this expression with respect to x and set that equal to 0. That's how you find where a maximum is. So this derivative is equal to 0. Solve for x. That's the position where you get your 0. And then D, what is the maximum field? After you find your value of x in part C, plug it into this equation and see what you get for your electric field. I'll post the answers and you can check against mine.